Hi, this is our second video of the series of 4. In this one we'll be looking at questions you saw in online tut test 2. So let's get started. The first question is a summation question. The question reads, using the data provided in question 3, calculate the sum of xi squared, where I goes from 1 to 5. So the data are given over here. Those are the data from question 3, and you're asked to find the summation of that. Okay, let's do that. So the thing key to note here is that xi is squared. Okay? So the first step in this process is to square each xi. Now, just as a side note, had it been the case that the summation looked like this, I equals 1 to 5 of xi squared, you would approach this problem differently. It's important to remember this difference. Okay, but as it stands, first we square each value of x from I equals 1 to 5. Remember, i's are given as the subscripts here, and then we sum. So what we have is 9 plus 25 plus 49 plus 81 plus 16, and that's the solution. Now, had the question specified the summation like this, then you would have simply taken the sum of the original values, 3 plus 5 plus 7 plus 9 plus 4, and then at the end squared it all. Squared the solution. Okay, so remember that distinction. Alright, let's move on to the next question. Another summation question. Here you're given some data, some values for x, ranging from x1 to x10, and you are asked to calculate the sum of xi minus x bar. Okay, now this was somewhat of a trick question. Some people in fact went ahead and did the calculation, but of course in this instance it is not necessary to do so because of this rule that we learned, which is that the sum of xi minus x bar is always equal to 0. And the reason for that, as demonstrated in lectures, is that you can break that expression up to two terms, sum of xi minus sum of x bar, and what you notice is that these two things are essentially identical. Why? Because what is the definition of x bar? X bar is given by 1 over n times the sum of xi. Another way of writing this equality is to say n times x bar equals sum of xi. What we did here was simply multiply both sides of this equality by n to get this equality. Okay, so now if we substitute this result into this side, we can rewrite this as n x bar minus sum of x bar. Okay, but we know x bar is a constant, and we know that the sum of a constant n times equals n times that constant. Therefore, this becomes n x bar minus in x bar, which of course equals 0, taking us back to this result over here. Now it doesn't matter what n is. In this case, n was 10, irrelevant. Doesn't matter what the number of variables is. The sum of xi minus x bar is always equal to 0, as we've just shown. Okay, let's move on to the next question. Okay, this one is a little bit more involved than the previous one. So this one asks the reason that the sum of xi minus x bar times yi minus y bar equals sum of xi into yi minus y bar, which also equals sum of xi minus x bar times yi, is because, okay, so why is it the case that these two things, that these three expressions all equal each other? Okay, so what we can do is just go through the derivation I showed you in class, that's also in your slides, which is to simplify this expression over here as follows. Let's say xi minus x bar times yi minus y bar equals xi times yi, just multiplying out the two brackets, minus xi y bar minus yi x bar plus x bar y bar. Okay. Now we can break up this expression into 4 separate terms as follows. Sum of xi yi minus, remember, y bar is constant, so it comes outside here, y bar, sum of xi minus x bar is constant, x bar, sum of yi plus, and here we have the product of two constants here, and the product of two constants results in a constant. Therefore, we can just write this as n x bar y bar, because the sum of a constant n times equals n times that constant. Okay, so now we notice that these two expressions over here can be rewritten, given our discussion on the previous example, as follows. Sum of xi yi minus n times y bar x bar minus n times x bar y bar plus n x bar y bar. Okay, so these two, the last two expressions here, the last two terms cancel each other out, right? Those two. There you have minus n times x bar y bar, and there you have plus n times x bar y bar. So we're just left with the sum of xi yi minus n times y bar x bar. Doesn't matter which of the variables you put first. Okay, now again we can rewrite this as follows. Sum of xi yi minus sum of yi x bar. That can be written as follows. Sum of xi minus x bar into yi. And we can do the same thing to get xi out of the bracket and have yi minus y bar inside the bracket. Okay, so what was the key feature here that enabled us to do this? So what we've ended up with over here is this expression up here, which z equals that. And also, as I just explained, we can write this as follows. Okay. So it's definitely not the case that the statement is untrue. A is clearly an incorrect answer here. What about B? Is it the case that the sum of yi times x bar equaling the sum of x bar times y bar is what enabled us to rewrite these expressions in the way that we did? Given what we've just gone through, clearly that is in fact the case, right? So if you consider this first term over here, that is identical to this term over here, right? Now consider this term over here. That one is identical to this term over here. Turns out in this expression there was a plus and there a minus. However, these two things are in fact equal. So this statement is true. And I believe E is the same one. So that too is correct. Okay, so far so good. What about C? Is it the case that the sum of yi x bar equals n times x bar times yi? Can we rewrite this like that? No, because we got rid of the summation, but we still have this indexed y over there. So that's clearly not right. What about D? Is it the case that the sum of yi x bar plus sum of x bar y bar equals 0? Clearly not. In fact, that's what we showed when we went through option B, right? That the two things are in fact equal. Therefore, the sum of them cannot be 0. Okay. So that explains how to approach this particular question. Next question. An experiment consists of 3 stages. A coin is flipped, a die cast, a card drawn from a standard 52 card deck. The suit of the card drawn is recorded. Okay, so there are 4 suits in the latter stage of the experiment. Okay, how many sample points does this experiment have? So here we have to apply what we call the MN rule in the lecture, right? Where you have different stages in an experiment. Different stages might have a different number of sample points. The total number of sample points of the overall experiment is then just the product of the number of sample points in the different experiments. So in this case, when a coin is flipped, there are 2 possible outcomes. When a die is cast and the number on the upper face is observed, there are 6 possible outcomes. And then finally, when you draw a card from a 52 deck card and you observe the suit, there are 4 possible outcomes, right? And in fact, the clue is given to you over there: hearts, diamonds, spades, clubs. There are 4 possible outcomes. So it's just a matter of taking that product, and that equals the total number of sample points in this experiment. Note that in this case we have m times p rather than just mn, right? And the same goes for any number of stages in a given experiment. In other words, we can expand this to q, to r, and so on, and so on, and so on. Okay, next question. Consider the experiment described in question 9 above. What is the probability, and that is the previous question that we just looked at. What is the probability of observing the following event? Heads on the coin, an even number on the die, a red card is pulled from the deck. Okay, so what do we know over here? We know that these are all independent events, these three stages. If we toss a coin and we find that it lands on heads, or the upper face is heads, it has no bearing. It tells us nothing about what number we can expect to observe on the die. And neither of the outcomes of those two stages of an experiment will tell us anything about the suit of the card or the color of the card drawn from the deck. Okay, so in this case we have so here we can just multiply the probabilities of the various stages given that they are independent. So we have a half for the coin flip, right? Because there's a 0.5 probability of observing heads on the coin. We have an even number on the die, again, that is a half, because there are 3 even numbers on the die. And 3 divided by 6 gives us a half. And then lastly, a red card is pulled from the deck. There are only 2 colors. And again, the clue is given to you there. Hearts or diamonds are red cards, and we know that there are a total of 4 suits. Therefore, there's hearts and diamonds together make up half the deck. And thus, again, we have multiplied by half. And that gives us the probability of observing those 3 specific outcomes given this experiment. Okay, next question. This question states, the stochastic error term in regression models represents what? 5 options are given. We are required to select the best of the 5. Okay, let's go through them one by one. A says the unseen variables that influence the regressors. Okay, usually in regression we are interested in variables that influence the regressand. Variables that influence regressors, it turns out, will be somewhat important later on in your econometric studies, but at this stage we are only interested in the variables that influence the regressors. So this doesn't sound like the best answer, but let's carry on and see. B, the variables that cannot be measured directly. Okay, so we cannot measure a variable directly, but perhaps it does influence the regressand, or the dependent variable y. But because we can't measure it, we're therefore not accounting for it. It goes into the error term, gets accounted for by the error term. Okay, that's plausible. So we'll put a little marker here. That's not too bad an answer. Is it the best answer? Let's carry on and see. C, all the variables other than x that depends on y. So usually in a regression model, y is the dependent variable and x, or the x's, are the independent variables. So it's usually y that depends on x. And this statement goes the other way. So that's somewhat nonsensical. D, given how we define conventionally how we define regression models. Okay, D, the variables affecting the regression that are not included in the model. That seems to comport with our definition of the error term. The variables affecting the dependent variable that are not explicitly included in the model. So that sort of makes sense, right? There's variation in our y variable, our dependent variable. Some of that variation is explained by variation in the x variable, but some of that variation is not captured by variation in that x variable. There are other variables that influence the dependent variable. And if those are not explicitly included in the model, then they are accounted for by the error term or the stochastic error term. So that sounds plausible. What about E, the randomness that cannot be accounted for explicitly by X? So this is an example of a phrase that sounds good, sounds kind of right, but it's really not. It just says the randomness that cannot be accounted for explicitly by X. What randomness exactly is being talked about? So it's really a nonsense statement that kind of sounds smart, but it's really not. Okay. So we've got two candidates, B and D. And as mentioned, D probably is closest to our definition of error term. So I would suggest that we go with D over here. And that's it. Thank you.